We can start. Okay, so I suggest you can open SYMICA, and various things we have studied in SYMICA, like how to set up the things in terms of setting up these transistors, and which model you have to use and how to run the simulation. That was the first lecture. The second lecture was the one where we have studied the transient response. In that, we have studied that if you are giving the input, output is depending on two things. One is the load capacitance multiplied by the resistance offered by PMOS or NMOS. So as you are increasing the width, the resistance is going to be decreased, and increment of the W of any of the device will give you better performance in terms of rise time and fall time. If you are interested to make the better rise time, you have to make sure that you are increasing W of this one, and similarly you can increase the W of NMOS if you want to have better fall time. So all these things we have learned. We also learned that with the label you can connect the wires, like in and in are shorted together. Similarly, like this VDD and this VDD are shorted together. We also learned that if you are using the GND-D, it's acting as a VSS, where it's exactly opposite of what we have VDD. So if you have VDD equal to 1.2 volt, then this GND, if it is D, then GND-D is acting as minus 1.2 volt, and that's why like this noise margin and other things were moving here and there. So that's why like we were getting the output as just always 1.2 volt. So what now our next agenda to understand is, the thing is, if you look at my tutorial, my assignment, in assignment, the first question is plotting the VTC. So let's understand that VTC is a DC characteristic where the input is not a transient input, but it has to be DC. So if I want to plot VTC, input versus output, I can do following things. I can remove this part, which is V pulse, and I can add the new voltage source whose name is VDC. Place that. But as we want this VDC to be changing and keep giving some name called V in DC, something like that, V in DC. And I have planned that I'm going to vary that such that I can plot in versus out. Note that right now we have some 500 femto of load, and these values are like this is 3 micro and this is 1 micro with 180 nanometer as channel length. Yesterday, like I got one message from one of the MTech student. Sometimes it might happen that if you are using 180 nanometer technology, and if you are trying to give lesser than the possible channel length, then definitely you will get some warning or some error. So do not do that. If you are giving 130 nanometer technology, so the minimum possible thing might be 130 or something like that. So if you're going much lower than that, then it is not giving you any kind of warning at a time, but when you run the simulation, it will give you that it's not supporting the compact models. So that needs to be checked. Okay, so in that case, you need to increase the channel length a bit so that you are above the minimum channel length, or maybe at least the minimum channel length. Okay, so we can start the environment. And now I'm not interested in the transient analysis. I have to be interested in the DC analysis. So I'm changing this to a DC analysis. And other than that, I'm interested in the design variable, which has to be varied, whose value I'm interested in 0 to 1.2 volt. So this is the minimum ground side and this is VD side. I want the increment of, let's say, 0.01, so that around 120 points is going to give me 1.2 volt, so that I can have a better curve. On top of that, as this is a sweeping variable, that variable has to be set, as we already know about this. So if I'm giving V in DC, I need to give some default value. Let's assume that I'm giving the midpoint as a default value. Then I run the simulation. So error. Okay. So error, you can see here type P of the element M0 unknown and M1 unknown. If such kind of error is there, it refers to the fact that NMOS and PMOS has some model called P and N, which has not been defined. So I need to add the model from the model library. I'm using 130 nanometer. Then if I'm going to run the simulation, I'll not get that kind of error. Now I need to plot on the main form, maybe add to the output. From output, you can see here the transfer characteristic is seen. Can I change the color or no? Okay. So you can see that as I'm increasing V in from 0 to 1.2 volt, output is going from 1.2 to 0. Notably here, x-axis is now changed to V in DC, whereas earlier time when we were running the simulation and when we were plotting, it was time. So now it's not time, because first of all, I am running the DC sweep parameter. One fact is that. Second fact is that all the values which are coming for a given V in DC, let's say 0 volt, there is a scalar values are available, which is only 1 point. So if there are scalar 1 points are available, then when you are going to plot it, you are going to see that x-axis will not be time, but it will be the sweeping parameter. However, if this if it is changing with time, then you cannot see that. Then you have to do something else so that you can get the output which has x-axis as V in DC. Sometimes you might be interested in such kind of diagram, but in that case you can plot it with the Lissajous pattern also. If you know that x-axis y in the xy mode of CRO, you used to do that. So here also you can do that if it is required to do with two different plots. So in that case also you can have V in versus V out. However, there are many other tricks through which you can find out. Now, as I told you, you can evaluate the function also. Like there are some functions are available over here, like a new expression. You can create some expressions over here, if you remember that. But these are very limited number of functions. So we are not going to use this one, but there is one good thing available for this SYMICA, which has many good features. You can go to eval goal functions. In eval goal functions, you don't have just arithmetic, but you can have the special operations also. Like I want to check that where this entire trace is actually crossing some value. Like I want to check that whether it's output when it's crossing 0.6 volt, I'll be happy. So you can see here, it's for input, it's 628.262 millivolt. That's the value available at the input side. So right now, the switching threshold, which is 0.6 volt of V out, for corresponding to that, input is equal to 628.62. If you want to check the same thing, you can do one thing. You can go to the cursor with the pointer, and you can see here at the down, whatever we are keeping our cursor, that x and y value will be written over here near to this 100%. So let's assume that I'm looking at 600 millivolt. So 600 millivolt is somewhere here. So you can see 600 is actually available at 628 when I was doing here at the x-axis. So that's what you can check and you can see. So this was one of the function to check what is going on. But now, as you know that if I want to make this whole transfer characteristic this side, because I want to make that V in DC, if it is 0.6 volt, I want to see that V out DC as a 0.6 volt. So there is a trick on that which you can plot it. Most of the people, they know it. So the thing is, I know that while doing such kind of thing, the technique says that if input and output are the values when both are becoming equal. So I'm shorting both of them just to make sure that right now I'm going to change the width of PMOS transistor, keeping NMOS transistor width as the stable one, which is 1 micron 180 nanometer, and I'm going to make this one as P width. For the time being, I'm removing. Okay, I can keep this also, not a problem. So what does what exactly is being happen over here is, look, if you look at those things carefully, it's like this. Means oh, means you can see that upside is diode connected, downside is also diode connected. Both are offering some resistances. So if both the resistances are equal, then I'm expecting this node to be VDD by 2 if both are equal. But right now, if like we can run it with whatever it was written, like let's assume that it's 1 micro. I'm not running any sweep parameter or anything. I'm removing all these things, and I'm going to run a simulation where there is nothing like a here when you are going to run it. Okay, asking input the field. Okay, because I have not given any input value, I'm removing this because that was the variable. Variable was not added. That's why it was giving the error. V0 is not found. Okay, this is V4, so I need to make it V4. I'm running this. Still, there is any error. What is the thing? I check and save. Parsing the input field. Where is the input?
Capital V, maybe.
Both are connected, right? Yeah. Anything left? Dinesh, what do you think?
The
Value
source
V4.
name capital V4.
Yeah, that's correct, right? It's V4.
Sir, maybe because you have given a DC value, assigned a DC value to the source already. VDC is equals to 1.2. And you are running a DC analysis.
I'm running, but I am not running any sweep parameter. Sweep is not there. Voltage source. I can remove this.
Sir, is source name case sensitive.
You're right. With the thing. You're right. It was case sensitive. Yeah, so we need to look at these things one by one, and then you can do that. Anyway, so right now, whatever the V out is there, you can see here using annotating the signal, right? So maybe we can plot that. Okay, it's there. You can see here, it's actually some value over here. So if you look at the cursor, the point, okay, not visible, but this is somewhere like you can see that this dot is between 581.92 milli to 581.93 milli. So it's not equal to 600 milli, because both the resistances are not equal when both are equal by 1 micro. As per the theory, you know that the current flowing through NMOS is equal to mu n Cox W by L, VGS minus VGS times VDS minus VGS square by 2. And in this case also similar, the VGS will be changed to VSG and VDS changed to VSD. And the only different parameter between these two is actually mu n. So mobility of PMOS is generally 3 times higher than three times lower than PMOS. That's why if you are going to multiply this W by L by 3, you are going to get the exact answer. But 3 is just a random number. I suggest we can find out that multiplying number through the simulation, where what we are going to do, we are going to find out which P width is going to give me output as 600 millivolt. So in that case, we are going to run the design variable whose name is P width, and it's going to change from 1 micro to, let's say, 10 micro with increment of something like 200 nano every time. So that is going to be run. Anything left? Oh, variable I forgot to add. So variable, I can add the variable. It's P width, whose default value is 1 micro. And then when I'm going to run this, you can see x-axis is P width and y-axis is actually the y-axis is the V output. Here you can see many points are there. Earlier you were seeing only 1 point. Now there are many points. So you have to find out the cross point. Maybe it's before 1.8 micro. So what I can do, just for a better thing, I can increase the resolution 1 micro to 2 micro, and I can increase this by, let's assume that by something like 50 nano. So then I can see more number of points, and 600 millivolt is around over here. You can use the cursor and you can see that. So here it's around at 1.55 micro. That's the value you can see here on the this side. X-axis value is 1.55 micro. So like after 2 digits of decimal points, there is no use of going further because it will not be recognized by the model. So you have to give something like 600 millivolt. You can find out same thing with the eval goal function. You can actually make the special operation, and you can use the cross function. In cross, you are interested in finding out net 23, which is output, and you want to check what is happening at 0.6 of the output. I'm referring to the output. If I'm doing this, I know that that value is 1.55845 micro, as we have seen over here, but this is through the function. So you can use that and you can find out that this value is now 1.55 micro. We will change this value, we will fix it over here, and we will remove this design variable, and we will keep before as it was earlier. So when you are going to run the simulation, you are going to, so still there is so you can see here there is only 1 point which is around at 600 millivolts. You can see that near to 600 millivolts. Still it's not 600 millivolt. If you are so much determined to get exactly 600 millivolt, you can run more parametric so that you can have exactly 600 millivolt. That width might be 1.58 micro or maybe 1.6 micro. Right? You can find out that with the smaller accuracy, and with the more number of points around 1.55 micro. Okay, so that was the first part. Now let's remove this and let's go back to the point where we were. So this was V pulse. Let's give this one VDC. And we are going to change this VDC to V in DC just to get the original VTC. So here default value, as I told, we can keep it 0.6. If you like 0 something else, you can do that. Here I am going to change the design variable to V in DC. Start value is 0 and value is 1.2 and points might be with 0.01. Left. Okay. So we have to select linear and we have to remove this 1.2 volts from here. Okay. So when we are going to do this, you can see what I did. V in DC. Okay. So this net might be the wrong one. I need to see what net is this one. With the Q, you can see that it's net and 2_1, but I was plotting something else. That's why that was the thing. So I can take this one to be plotted on. When I'm going to netlist and run, I'm going to see that. You can see this characteristic is actually when it's 600 millivolt. From here, I can use the cursor so here you can see around 600 millivolt. I am seeing output as 591 millivolt. So something 594 millivolt. So accordingly, you can tune and you can find out. So one of the given assignment is you have to create a characteristic where this point will be exactly at 0.6. So you have to work hard and you have to get the 600 millivolt. And there might be like one point where I asked to change this, curves dynamics like this is changing with slope of -1 and this is changing with slope of -1. At these points you can shift here and there by changing actually the capacitance and W by L. So those things you have to do it on your own. So I'm keeping to you so that things will be like explored in a better way. Sometimes otherwise you will be doing the simulation only the way I am doing. Okay, so now this was one part, we DC and all. Now it's a completion of first assignment. First question where VTC was given to you. Other than that, you might have interested to find out some more things like rise time, fall time, and all these things, where you need to know the transient analysis rather than DC. So in that case, you can give these values from 0 to let's say 1.2. This is logic 0, logic 1. Period I am going to give, let's assume that it's 1 micro. Delay I am giving as 0.5 micro. And the pulse width is around 0.5 micro. So this pulse width, make sure that this becomes square wave. Otherwise, if you give something else, this will become actually rectangular wave. So accordingly, you can design it whatever you want to give. Okay, so now if that is the case, last time we did this analysis and we also learned that you can do the transient analysis, right? Where the start time and stop time is there. Start time is of course 0. And if you want to change the start time, there must be some start is already over here. So the before start, other things will not be actually saved. So, but as the time being, these things are not required to change. Stop time, if it is pulse, the square wave is of 1 micro, you can keep something like 10 micro to see the output for 10 cycles, right? We don't require this parameter, so I removed it. When you are going to run this one, you can have a window, whichever you want to run. Generally, I will be interested in plotting input and output together just to make sure that everything is fine. So here you can see things are pretty fine. You can scatter the traces. You can see that what is. So you can see TPHL and TPL can be found out with the difference between this 0.5, 0.6 volt from input to output, and that value will be your propagation delay. For this will be TPHL. If you are interested in TPLH, that will be at other side here. Here you can find out the TPLH, which is from. So you have to subtract the time from this input of 0.6 to the output of 0.6. So that is what you can find out. Now, there are many good things are available, because you can do all these things through the cursors and through the manual eyes. But there are more functions are available, like Golf functions. You can go here in the special operations, like you want to know what is the rise time. So I am interested in rise time of output, which is N21 is the output. Look at this. So I'm interested in N21, and I'm interested from 10% to 90%. Look, rise time is the one when you are interested from 10% value of V out to the 90% value of the V out. So in this 1.2 volt, 10% will be 120 millivolt. So the first point you can see here, that's the 10%, and the next one is the 90%. So out of 1.2, 120 millivolt needs to be removed. So it will be 1 volt, right? So when you are going to do this, you will have the answer. You can see that the rise time of your output is 2.62328 nanoseconds. Similarly, you can find out the fall time, you can find out the settling time, and many more things. But note that wherever the commas are given, you need to feed those values, and for that you need to go to maybe the help file. Just for getting the help, you can go here and you can go to the SimProbe user guide, where all the functions are given. So here you can see that all the functions are explained. You have to look at them one by one. So I cannot discuss all of them. So you can do that and you can find out this. So now there is one interesting thing. Okay, other than BTEX, how many have heard about eye diagram? Communication must be knowing this, right? Yes or no? Or eye diagram? You know about eye diagram?
No, sir.
No. Okay, but that is expected. So I suggest you please read something in communication side. People are using this eye diagram. So eye diagram is the one. I'll maybe explain the theory when I'm going to use the starboard. But eye diagram is the one. If you are looking at this output, let's assume that you are. I'm not. Okay, so you can see here. You can see that output is going from 1 to 0, 0 to 1. Now let's assume that you are only interested from 1 to 0 only. So plot 1 to 0, then again whatever is here 1 to 0, plot it again here, starting from 0 point. Then again going from 1 to 0, means from this point to completely this point, you have to plot it over here. Means this side, where all the 1 to 0 will be on top of each other. Everything will be on top of each other, going from here to here. Similarly, when you are going from 0 to 1, means this point to this point, the entire thing will be plotted on top of this one. Like earlier, we already plotted 1 to 0, all the cycles, and another one we can plot it here, which will look like this one. Sorry, any question? Okay, so you might be plotting 0 to 1 like this. So when you are doing this, you might see that going from 1 to 0, when you are looking at all the transition 1 to 0, might not be at the same place, and you might see that there is a deviation. But what we have done till now in this analysis, most of the things are actually like going from 1 to 0. They must be aligned with the all the instances. Notably, all these 1 to 0, if you are looking at only 1 to 0, those are known as bits. So if you look at 1 to 0 bits, and if you are plotting them, they will be exactly coming on top of each other. And similarly, 0 to 1, it will be coming on top of each other. So what I want to say, you are going to see something like this. If you are interested in eye diagram, I am telling that the level is 600 millivolt, and I am drawing the both. Okay, so I need to select the trace also, which is n to 1, and in that I am interested from 0 to 10 micro. And as I told you, like all these things for eye diagram is more number of bits. Generally in industry, if you want to find out the eye diagram, you should have at least 1000 cycles, or maybe sometimes more than that. Like some people are taking 50,000 also. So depending on the application, just to get the accurate result. But here only for 10 cycles I am showing, but afterwards I'll run the simulation where more cycles will be there. So how does this eye diagram look like? It will look like this one. Look at this. As I told you, this is going from 0 to 1 and going from 1 to 0. It is looking like this. As I told you, and the whole picture which is coming in your laptop, it's known as the eye diagram. Now I'm going to do some crazy thing over here so that you will understand that how these things are changing. But I'm adding one sine wave. I'll tell you the reason maybe after completing this, when we are going to run the simulation. So amplitude of this one, I'm keeping 120 milli with the frequency of, let's say, 101.789 mega. This is, by the way, some random number. By the way, what I'm giving is some random number so that you can see the effect of this eye diagram. Here again 120 milli, but I am giving here something like 78.9856 mega. Now I'm going to run this. What is going to happen? Note that, just for your information, what I did here is I added some noise source in VDD. As you know that VDD is not generated straight away 1.2 volt. It's generated by some rectifier circuit where it has some pulsating DC. So it has some AC potential is also there, which is having some frequency. I gave some frequency with the fact that this VDC is changing by 10% higher side. So I just gave 120 millivolt at the higher side. So that is what I did. And for the case of ground, there might be the ground which is having ground bounce or the substrate noise. So that noise is also something like plus or minus 10% of VDD. So I kept VDD over here. and I gave some frequency. So depending on what frequencies are there. So these two are the noise sources. I just kept it so that you can understand its effect. So when I'm going to run this, now look at the output. So output will look like this one, first of all. And what you're seeing here, look, the output when PMOS is on, we know that output is equal to VDD, where VDD is nothing but VDC plus some noise source. So that is what we are seeing over here. And similarly, ground is also having some noise. So it looks like this one when NMOS is connected. So now if you are going to see the eye diagram, then things will change. So the select trace of N to 1 and going from peer to peer with 600 millivolt, and I'm interested in both. So can you see here when your output going from 1.2 volt to 0 volt, those plots are not exactly coming on top of each other, right? And similarly, if you look at the plot which is going from 0 to 1, it has also some width over here. Now maybe I can do some few more things, like instead of 120 millivolt, there might be happen that just for this is only for the understanding purpose, by the way. So I'm giving 300 milli, and this one also like something like 300 milli. What is going to happen? You might see that there are more degradation, by the way. Earlier it was seen that input to output was very nice, but now this is getting worse. This is logic 0 is trying to go towards logic 1, but still I kept it in the intermediate place where it's undefined. So still you can identify logic 1 and 0 very easily. And when you are drawing the eye diagram for N to 1 and this one for 600 milli, because that's the middle point, and we are interested in both. So you can see here that similar thing we are seeing, but let's understand this. You might, those people who have studied communication in their BTech or those who are in MTech communication, you might have heard that the eye diagram, this is known as, by the way, eye. There are two eyes are there. One is going from 1 to 0 and one is going from 0 to 1. Both are combiningly known as eye. So it is generally the guideline that eye should be open enough. So here you can see eye is seen over here, but eye is still open. If eye is not open, means this logic 1 is coinciding with logic 1, then it's dangerous for us to define logic 1 and 0. So in that case, it's not a good design. Means you have to design your system such a way that it requires to have lower noise and better amplification in the as an amplifier. Similarly, you have to make sure that this eye has to be wide open. There are two things. One is wide open from this point to this point, x-axis. So that tells you that in it has a better bandwidth. If it is smaller and coinciding each other and eye is not open, means your output does not have proper bandwidth. What I mean to say is this one. Let's assume that instead of this one 500 femto, if I make it something like 10 pico, what is going to happen for the same analysis? Output should be charging and discharging, right? As we already know. You see? Okay, maybe I can take more value so that we can see the problem. If it is okay, 100 pico might be too much. 50 pico. So you see here, and if you draw the eye diagram for such a case, Look at this. I can maybe run for maybe more cycles. This is not. So as I told you, it requires more number of cycles. So let's assume that I'm making for 100 cycles. But in reality, if you want to find out some real parameters, you need to run at least something cycles in thousands, so that you can have some accurate results. Right now, I'm not telling you what the results names are, but at the end, I'm going to tell you when we are going to have the real picture. So this one N21, when you draw that, maybe it's taking time. Hmm? Is it taking time or no? There are lots of points, so maybe computer is also okay. So here you can see that, okay, laptop is literally crying with these so many points. You can understand you need a good system when you are doing all the simulations in industry. Okay, very good. It takes time. So what my point was, you have to understand one fact that now you can see here the eye is almost closed. Eye is almost closed. It's not open because the load capacitance is too much. You can reduce the, you know how to fix this RC time constants, right? So when you are going to fix this eye will be open enough. One more thing, this digital logic 1 and logic 0 are also coinciding with each other. If you want to take y-axis opening, means this side opening, then you have to touch W by L, and you have to make sure that your inverter has proper value of W and L, so that logic 1 and 0 are exactly logic 1 and 0. And if you want to open this X side, which is actually the time, then you have to make sure that the time constant is enough. So your eye should not be closed. That is the main thing over here. Now let's go back to the original function, where let's say I'm running for 100 microorbit, but this is not, this function is having enough value so that you can have a proper output. So I'm not saving this. Okay, so now when I'm going to run this, notably I can change the option to maybe liberal also if it is required, so that number of points will be reduced. So now if I'm going to run this, I'm going to see something like this. And along with that, I'm interested in plotting the eye diagram, which is starting from 0 to 100 micro, is going to 600 milli. I'm interested in both of them. Trace is V21, and I'm going to plot that. I'm going to see something like this. So you can see here, going from logic 1 to 0 and logic 0 to 1 in an eye diagram, there is at 600 millivolt. You can see that there is a width from there is a width going from this point to this point. So at 600 millivolt, you need to measure that, and that is known as jitter. Or there is another similar name, which is known as time interval error, TIE. So if you want to find it out, you need to look at the 600 millivolt going from 1 to 0 or going from 0 to 1. Whichever is the higher, that is going to be declared as a jitter. Note that when there are various kinds of jitter are there, but in this case, the power supply has been considered as faulty one, and it has some extra noise sources given at the VDD side and given at the ground side, and that's why you are seeing such kind of jitter, and that's why the name of this jitter is power supply induced jitter. Notably, all these things which we are doing, it's a deterministic. So this is the category of the jitter which is known as deterministic jitter. However, if you are interested in finding out the probabilistic or the statistical jitter, you need to add the probability functions or the statistical models of PMOS and NMOS, and you can have the jitter arise from the device property. So one can do that, but that's not part of this course. You can extend this to maybe analog, and you can understand further. In that case, the name of this jitter will be changed to phase noise, by the way. And phase noise is d phi by dt. The same thing is happening here. This is also time interval error, and it's changing with respect to time. So that is also d phi by dt. Okay, so this is for your first assignment, where first question has following things to find out. One is VTC, one is rise time, fall time, maybe settling time, and other things like you need to find out the time interval error or jitter. So that you might not be seeing if you are giving just a square wave as an input. If you want to introduce that, you need to add such kind of noise sources, or you need to add the statistical models of PMOS and NMOS, and you have to run the noise analysis. Then you can have the device characteristic, which will have the time interval error. So that was the next part. And after that, with the different value of capacitors, I asked to simulate it and just to find out the same thing with different values of capacitor, how it behaves. Other than that, you need to find out the W by L of, when I'm saying that design an inverter for a VTC where V in and V out are equal. In that case, when I'm saying design, means you have to design the W by L of PMOS and NMOS. When you are finding out W by L of PMOS and NMOS, that's the answer of your assignment. You need to add some text also, because your understanding matters a lot. So not just running the simulation is enough. You have to make sure that you understand that also, and around that you have to write some text. So that you need to do. And one of the question is that you have to prove that this inverter can be used as class AB push-pull amplifier also. So you can run some of the required simulation, and then you can submit it.